Hello, IB. We're getting into 18C, which is the fundamental theorem of calculus. So we spent the last few months looking at differentiation, which is the first part of calculus. And then we just discussed the last 2 days how finding the area under a curve is using an antiderivative. And when we put the two of those together, we wind up noticing how they're linked together. And because those are the two main parts of calculus, the link between them gives us the fundamental theorem of calculus, or the fundamental idea behind calculus. So what is calculus all about? So let's just take a look back at what we've done so far. In 18A, we looked at how the limit of the area sum using rectangles under the curve is the definite integral. So we looked at how we could find the sum of an infinite number of rectangles. So if we divided this space into infinitely many small rectangles, we added up those areas together, we wind up converging to the actual area under the curve, known as your integral. A definite integral because you're given two endpoints, A and B, to find the area. In 18B, we noticed how if we have a definite space, especially we started with shapes that we knew. So if we took straight lines, constant functions, diagonal lines, so linear functions, and we tried to find the derivative, we could try to find the area under the curve, we realized that we have an antiderivative when expression to use to find the area. So 18B was all about the antiderivative and noticing how if we derive a function, we get the derivative. If we antiderive the function or take the antiderivative, get back to your original function. So some of the rules that you guys have already covered, a little summary for us, is if you have a base with a power, so a polynomial, we wind up adding 1 to the exponent and dividing by that same exponent. We add a constant c as a possibility, because when we take the derivative, it goes away. So if we take the derivative of this expression, we get back to the original. So again, it links the derivative with the antiderivative. We had a brief discussion in class about what happens with 1 over x, because that is x to the -1. So if I just added 1, then I would get x to the 0, which is not going to work for us. And we have to think back to how we got 1 over x. So what did we take the derivative of to get 1 over x? And that goes back to the natural log function. We also looked at a few examples where e was your base, and the derivative of e is e to the x. So that would mean the antiderivative is also e to the x. So if I were given anything besides e to the x, what if I had a coefficient there for my exponent? So e to the 2x, your general antiderivative would wind up being e to the 2x, all right? But then we would have to divide by 2, and we'd have to add on that possible c. So to make a general expression, I'm going to get rid of that 2, and we'll take that 2 and make it any number that we'd like. So let's say it's e to the kx, then we'll keep e to the kx, and we will divide by k. All right, so if we did take the derivative of e to the kx over k, even if we have that c there, all right, the derivative, so I'll add brackets there if we have the c. So the derivative of e to the kx over k would be e to the kx over k and multiplied by k. So the k's would cancel out, and then your c would also wind up going to 0. So we'd come back to that original function that we started with. These are all the ones that we've discussed already. You can also think about how this would apply with sine and cosine and tangent, and then eventually we'll also get into the chain rule. So even if we start with something like ax plus b raised to the nth power, all right? So think about that ax plus b could be 2x plus 5. So let's look at that for a moment. Let's say this is 2x plus 5 raised to the 2nd power, okay? If I think about what happens when I take the derivative of this, I would normally do the same thing that I do with a polynomial, but I'd have to multiply by the derivative of the inside function. So I'd have to multiply by that 2. So if I were working backwards, let's say I added 1 to the power, and I divide by that same power. Normally I would multiply by the derivative of the inside, so now I'm also going to divide by that additional 2. All right, so I'd also multiply by a 2. So what I'd wind up with is 2x plus 5 to the third, all divided by 6, plus a possible constant. So let's see, if I did take the derivative of that, would I get back to my original? So if I had 2x plus 5, all raised to the third power over 6 plus c, what would happen if I took the derivative? So 3 multiplies by my coefficient. I get 2x plus 5 to the second power, which is what I wanted, multiplied by 2. Let's see what happens here. 3, 2x plus 5 to the second power, excuse me, all over 6, and multiplied by the 2. So 2 and 3 make 6, so those will cancel with the 6, and I do wind up just getting back to 2x plus 5 to the second, which is what I started with, right? So we can already even look at a little bit of the chain rule here, just the beginning, by saying I'll keep that ax plus b, I'll add 1 to my power, and then I'll also wind up dividing by n plus 1, and I'll also wind up dividing by a. All right? I'll scooch that 3 down, just so we don't have that in the way. So just take a look at what we can do already, and we'll be using these rules for the first few days of this chapter, and then we'll wind up adding on some of our other rules as we go. So that was a recap of 18A and B. In 18C, we look at how the two are connected. So how does your derivative and antiderivative? We've already discussed a little bit how they're connected algebraically, and we've been looking at a function. So visually, we've been looking at how the area winds up connecting. And in class, we actually did this exact question. We said if your function is y equals 5, and you wind up blocking off the area between two values, so here they just call them a and t, you get this rectangular shape. So the width of the rectangular shape is t minus a multiplied by the height of this rectangle is 5. So we get 5t minus 5a. In class, we just called this b, and then b, and we had 5b minus 5a. So what we wind up getting is the antiderivative, this expression of the antiderivative evaluated at b, minus the antiderivative evaluated at a. All right, and then we wind up getting noticing that this is your antiderivative expression, plus a possible c on the end. So using that b instead of the t is the same thing that we were doing in class. We also wound up going through a similar example with a trapezium. So if we have a linear function and we wind up blocking it off between a and t, we get a trapezium, and we notice that we also got an expression for the antiderivative. I'm going to scroll in case you'd like to try this one again on your own, very similar to the one that we did in class. And you still wind up with your antiderivative evaluated at your two endpoints. So what we decided from the investigation we did in class was that the way the two are connected is that if you take the integral from any point a to t of a function with respect to the input x, we get the antiderivative evaluated at one endpoint minus the antiderivative evaluated at the other endpoint, and the difference between the two. And we're saying that capital F is your antiderivative. So if you took the derivative of your antiderivative, you get back to your original function. So linking those two ideas together makes your fundamental theorem of calculus. All right, your textbook goes a little bit more into detail on page 451. We have discussed the basics of it here and also in our class together. So let's take a look at how we actually lay out our work for something like this. So laying out my work for part A, use the fundamental theorem of calculus to find the area between the x-axis and y equals x cubed from 0 to 1. So we are talking about the integral from 0 to 1. Our function is x cubed with respect to x. So we are saying that I want the antiderivative expression evaluated at 1 and the antiderivative expression evaluated at 0, and I want to subtract the two to find my actual area under the curve. So what I'm going to do is take the expression for my antiderivative. So x cubed is now going to be x to the 4th divided by 4 minus, evaluated between evaluated between 0 and 1. So for you guys, your notation, you guys can use hard brackets. Sometimes you'll also just see a straight line from 0 to 1, or you'll see something like this, x to the 4th over 4, and you'll see hard brackets. And then you'll put the 0 and the 1 to the right. The 0 and the 1 just remind you that you now need to substitute the 1 and substitute the 0 and then subtract the 2. So whether you use this left notation or this right notation, the 1 and the 0 are there just to remind us that we have not finished. We actually do need to substitute in the 0 and the 1 value. So what we'll do next is then take the 1, so 1 to the 4th over 4, and subtract 0 to the 4th over 4. So for this one, we'll wind up just getting 1/4 minus 0, so just 1/4, and we are talking about an area, so we are talking about units squared, or squared units for this. All right, guys, so our last check is just double check ourselves using technology, or if a question asks you to do something with the derivative, or with the antiderivative, or with the integral, you guys will wind up possibly needing to do this just to speed up the other steps along the way. So we're going to get the integral using your multifunction button here. We'll go ahead and put in from 0 to 1, 0 to 1 of x cubed. And we have to put in with respect to x. And just make sure that we get the same answer. All right? So double check yourselves. Remember, we're talking about areas, and we now have squared units. Please make sure your notation is neat. So either choose to use the straight line or use the hard brackets, but you do have to show what your antiderivative expression is. You do have to show evaluating at both endpoints and then getting down to your final answer. Go ahead and try B and C on your own. Check with technology to make sure you're on the right track, and that way we've got a good point to start at next class. All right, guys, have a good night.